Welcome to live patching, a down in the trenches view. I'm Newman. I want to start this talk by some disclaimers. I'm very much not the expert on live patching. I'm somebody who was running a virtual private server company and decided that live patching seemed like a pretty useful technology. And so I decided to try it out. It seemed to work. And so now I'm going to talk about it now. I would say that incorrect live patches can cause crashes and data loss. So if you're going to try anything from this presentation, you probably want to try it in a test environment first, not in production. Don't do what I did and crash a single server because you didn't do adequate testing in advance. All right. Agenda. I'm going to start with some terminology. I'm going to go over why live patching, talk about some types of live patching, and then the bulk of this presentation is going to be about building live patches. So terminology, because I'm not sure where everybody in the audience is starting from. This is all probably pretty basic for most of you. But with hypervisor, it's a system that runs virtual machines. Common examples are KVM and VMware. Xen is also a type of hypervisor. CentOS and Ubuntu are Linux distributions. binutils is a suite of utilities that includes readelf and object dump, which can be used to look at program sections. So an executable on disk will include a section for machine instructions called text, or it will include something for initialize data in the data section. With newer versions of GCC, there's also compiler options, fdata sections and ffunction sections, which allow your functions in your data to go into their own sections, which happens to be handy while you're building live patches. And then finally, microcode is, I would guess I'd call it firmware that goes on a microprocessor, such as an Intel or AMD. A lot of times when you want to do security updates, or at least some of the time when there's a security update, often related to side channel attacks, there might be a new version of microcode, and you might have a live patch that depends on that. Next, I want to talk about why live patching. So, problem statement. I want to apply a software update to a kernel or a hypervisor, or in some cases, a core user space program, and I want to do this with no restarts or reboots required. And to go over why live patching, I'd like to talk briefly about some of the alternatives to live patching. Reboot is an obvious one for applying a software update. In the case of a database server, unless you attended one of the previous presentations, this might take on the order of hours. When I was doing my virtual private server company, we would have it where it might take up to an hour to bring down the virtual machines, reboot, and then bring the virtual machines back up. kexec is a way to avoid the hardware part of that reboot, but you still have the overall time associated with the reboot. Redundant services, so behind a load balancer or some kind of high availability solution, allows you to perform a software update on one of the systems without having any downtime to your customer. And then finally, in the case of virtual machines only, there's live migration. So you can have your unpatched hypervisor running multiple virtual machines, your patched hypervisor that maybe doesn't have anything on it. You use the live migration protocol to copy over the virtual machines one by one. When your old machine is evacuated, you can go ahead and bring it down for your software update. Given these alternatives, why would I look at live patching? Well, at least in the case of virtual machines, not all operating systems are live migration capable, so you'll try to live migrate them, and you'll have to perform a reboot instead. Live migration is not always as well tested, so you can have bugs that occur after the migration, and then you have to reboot the virtual machine anyway. And then finally, live patching is very fast to apply compared to pretty much all the other options that I mentioned. So I would say that if it takes any effective time at all, like we're talking about the order of probably tens of milliseconds, which is much faster than doing a reboot. Other than redundant services, I would say redundant services obviously would be comparable, but you can perform live patching without loss of redundancy. Okay. Any questions before I continue? All right. Okay, types of live patching. And by this, I just mean conceptually, like how I would perform live patching. So I have edit in place where I could overwrite an existing function with a new one. So generally, when I perform live patching, when I talk about doing a live patch, I'm talking about patching a function. I'm not talking about patching individual bytes or a module. Okay, so in this case, I have a function here that I want to overwrite, want to make into this one, and if it happens to be the same size or smaller, I can just overwrite that in memory. I haven't found any examples of doing edit in place that I'm aware of. So then another possibility in theory would be splicing, which would be if you could find all your callers to a function, edit them to point to the new function. You do have a problem with function pointers that are pointing to this original memory. Trying to find all those function pointers and edit them might be a challenge. So again, I don't think that I'm not aware of any examples of somebody trying to use splicing for doing live patching. Then the final method I'd like to talk about, which is the method that people actually use, is a trampoline, where conceptually you're just inserting a jump at the beginning of the original function to point to your new function. In Linux, this uses, I believe, the ftrace framework. And then you have the advantage that your new function can be any size. This does have the disadvantage compared to the other ones of having some overhead, but it's fairly minimal. And as far as I'm aware, as I said, I'm pretty sure that all of the live patching technologies use this. All right, so the bulk of my presentation, because as I said, I'm somebody who built and applied live patches in production. The bulk of this is going to be about building live patches, and in this case, all the debugging that went along with building live patches. So there are a number of different implementations, and if you come out of this talk interested in the live patching, but it's not your dream to be a kernel engineer, I would highly recommend you talk to one of these companies about live patching solution for your system. So I will specifically be talking about Zen and also Kpatch, because those both had pretty good open source implementations, or at least they had open source implementations I could find. So next, your build environment. You really should use the same compiler and the same compiler options as the original build. If you don't do that, Kpatch at least will warn you. I'm not sure that the Zen live patch build tools would. I would say that it's easiest to self-compile and preserve the original environment, so probably using mock or Docker or Chroot or whatever it is, just something where you're not continually trying to keep that build environment up to date. Then there's a question of what can be made into a live patch. And again, this may vary between different implementations, but I think that at the base, the basics are generally all the same, what is easy and hard. So what I found to be easy was changing just the logic within a function. You can also add variables, so add a global or a static variable. Harder would be changing an existing data definition. So perhaps if you have a bit field and you want to add bits to that bit field, but you aren't changing the size of anything, this should, in theory, be possible with some help that I will get into in a bit. Hardest, I would say, is if not impossible, would be changing the size of a data structure changing the initialization code because the initialization code is already run, therefore you can't live patch it, or changing parts of the live patch code itself probably are not necessarily advisable. And as I said earlier, some of the live patches you might want to generate for security reason might use new microcode. Well, Linux and newer versions of Zen can load new microcode at runtime in case you weren't aware of that. Okay, so now I'm going to go through a few small code examples. Again, this is from the Zen code base, so it may not be generally applicable. But here I have in the I'm patching something in the init section, schedule init. I'm just adding a print k. Do you guys think it'll patch? Raise your hand. All right, yeah, definitely. You're totally right. No, it's explicitly ignoring the init section. Even so, that code already ran. That, you know, there's nothing to do there. Then here I'm adding a variable, and I'm calling it from a function called scheduleID, so stupid code. But do you think it'll patch? Raise your hand. Yeah, it actually successfully patched, and I ran the code that exercised this patch. And here's, oh, all right. Here's some of the output at the bottom. Okay, now I have a structure that I'm changing to be, that used to be const. Now I'm removing the const. Do you think that'll work? Nope, definitely will not work. So symbol change sections, so from the read-only to the not read-only, so definitely doesn't work. And then adding on to a structure, and there are statically declared instances of it. Will it patch? So again, the answer is no. So that's because of an object size mismatch. So I suspect, but I haven't tested, so I don't know for certain, but I suspect that if you didn't have any statically declared instances and you were just, you know, doing dynamic allocations, that this would only be function changes. I could be wrong, and that might actually generate a patch that, of course, would not work properly. I could be wrong there. Unfortunately, I didn't have time to get that far. So one of the workarounds that's available for things that will not patch properly is hooks. Both Zen and Linux have concept of hooks. You can make changes potentially before, during, or after a patch is applied, or revert hook. You can make changes right before, during, or after a patch is reverted. So you can use this for sanity checks. You can use it for modifying data. So if, for example, you wanted to add that bit to that bit field and you knew where all of the instances of that structure were in memory, maybe you could go back and backfill, you know, some of what that bit, the definition of that bit is, as an example. Another workaround is shadow variables. So conceptually, this is adding a variable onto a structure. In Linux, there's a shadow variable API you can use to do this. So I can have multiple shadow variables associated with a single structure, or just an address, really, in memory. And Zen, unfortunately, there's no shadow variable API. You'd have to hand roll whatever it is you were doing there. And alternative instructions I mention only because this is the reason that I had my one crash in production. So different versions of CPUs have different capabilities, different instruction sets. Generally, like when we do a binary for x86, it's the lowest common denominator. So alternative instructions is a framework for patching in the correct instruction based on the instruction set. So for example, if a processor has this supervisor memory access protection, I believe, but not all Intel processors do, it'll patch in the correct instruction. in order to protect or unprotect memory. And it does this, with a Linux module, it would do it when it loaded it, or in for Zen, it'll do it when it loads the live patch. And this really needs to be run as part of live patching, or like me, you will discover that you've encountered a memory access violation. So the bug, I was apparently an early adopter of the live patching in Zen, and I did not test on the specific processor that I was going to apply the live patch to, and they weren't handling the features to apply the alternative instructions correctly, so I encountered a bug there where the alternative instructions weren't applied correctly and had my crash. So that's why I mention it. Any questions before I continue? All right. Okay, moving on. So patching Zen specifically. So I want to talk a little bit about the consistency model. So unlike Linux, patches are kind of applied all at once in Zen, so there's no concept of I've applied a patch to one virtual machine or another machine, does it all at once, does it with interrupts disabled. And you probably shouldn't patch anything in the call stack while the live patch code is running, because the old code will continue to execute. So the process of applying a patch in Zen, so you can upload the patch, it allocates memory for the patch, it resolves the symbols, and then it applies the alternative instructions. So when you go to apply the patch, there are work queues in Zen, so it schedules work to apply the live patch. Then within the code, like in the idle loop, the CPUs will check for live patch work and then kind of all rendezvous at a specific point in the code is what they call it. The first CPU there applies a patch, so it'll run the apply hooks. Zen does not have I believe it's the F entry that puts the in Linux that puts the no ops at the beginning of the function, so it doesn't have that, so it has to save the old instructions before it overwrites them, so you can revert the patch, and then it overwrites the beginning of the function with a jump, so a jump from your old function to your new function. So for the test patch, I decided to do was an actual security patch, Zen Security Advisory 401, which there was a race condition whereby a safety TLB flush is issued too early. In any case, I picked this because there was a total of one function patched, get page type in mm.c. So the process of building the patch, I will note, just in case you're familiar with Kpatch, the Zen live patch build tools are based off of Kpatch. So here I give the source to Zen, I give the config for Zen, I give it the path to the patch. Then because in Zen, when you stack live patches, it wants to do a safety check to make sure that you're stacking the patches as expected. So you'll give it a path to a dependency of that will either be your previous live patch or Zen itself. So here I'm giving the build ID just of Zen itself. There's a similar check for the build ID of Zen with this Zen depends. Then I give a path to Zen symbols, which is used both as a sanity check to see is the function that I'm patching actually in the original version of Zen that was built. And also the size of the patch is pulled from, the size of the function is pulled from Zen symbols. And then finally I give it the output directory. So building my live patch, it builds everything. It has this reading special section data, which will do things like, I believe, pull the size of the alternative instructions, among other things. I didn't look at it in that much detail. So to apply the patch, there's a shim in between make and GCC that will take any source that is built and copy it off to a special directory. Then it will unapply the patch and do the same. And then it will compare the two using create diff object, which is part of the build tools. And so it'll do effectively a binary diff with a number of safety checks to make sure that what you're generating can be an actual valid live patch. And one thing I would like to point out is that if you are adding a source, which you think would be easy for it to add to the live patch, at least for Zen, if you add a new source file, it doesn't get included in the live patch. So don't do that, as I discovered a little bit ago. All right. This was not my first experience. My first experience actually was that nothing worked. So the last time I seriously used this was CentOS 6 and Zen 4.8 as of 2020. So Zen 4.14 and 4.16, whether it was CentOS or Ubuntu, it didn't work out of the blocks. So I did a bit of digging. I was able to generate a patch for Zen 4.13, and that's still security supported, so I figured good enough for this presentation. I asked about it on the Zen mailing list, and turns out that master and some public patches for the live patch build tools, that all works together, and I was successfully able to create a live patch for that, but I wasn't able to successfully backport to Zen 4.16 or 4.14 cleanly. So as far as I know, nobody has tried to build live patches for those versions. Hopefully when Zen 4.17 comes out, that'll have support. Then problems I encountered, I needed dwarf debug info re-enabled. So the dwarf debug info had been disabled. I encountered a seg fault with create diff object. That was fixed upstream in Kpatch, so I backported that successfully to the Zen build tools, and then I had a change function not detected. And I'm mentioning all of this only because I want to emphasize that there's kind of a strong dependency in between what you're building, your live patch build tools, and the version of the compiler. So then I tried to load my live patch, and it failed because I have an ABI breakage. So having fixed the ABI breakage, I was able to successfully upload and apply my live patch, but then when I went to go take a look, it had patched a lot more than I expected. So rather than patching my one function, it had patched eight functions. I took a look with object dump, and indeed those were all defined. So now I needed to do some debugging. And I happen to know from former experience that log messages can be a problem with generating live patches. I think more so with Zen than with Kpatch, because Kpatch has some logic to try to filter out changes to the log messages. But having fixed my formatting, fixed that, my new object dump, I had just the one function patched, and it successfully applied. And so we've generated a live patch for Zen. Some of the other problems I encountered previously was that with CentOS 6, the compiler would kind of randomly insert no-ops into the code, and I would manually look at those and try to figure out what was changed, and I didn't really observe anything changed, so I carried a local patch that would allow me to filter out those functions from my live patch, but I haven't yet observed it on CentOS 7, so I'm hoping that that is an upstream bug that has been fixed in GCC. And then the final thing for Zen that I'd like to mention is there is a payload limit. So this applies to Zen only for the most part, I would say. If I try to generate a live patch that is larger than 2 megs by, for example, inserting a space at the beginning of a whole bunch of files so that we get those debug line message changes, it rejects it with invalid argument. That's because there's a check for live patch max size, which is defined at 2 megs. And I have not tried live patching that to make that larger, just so you know. Then finally, I'd like to finish with patching Linux with Kpatch. So I didn't go into this as deeply as I did with Zen. The consistency model. So for the consistency model, there's a live patch framework in Linux that is somewhat common between the different tools. So with this, patches are applied on a per task basis. The kernel will, when you go to apply the patch, the kernel will check the stack of a sleeping task to make sure that there's nothing being patched in the stack, and if there's nothing being changed in the stack, it'll go ahead and apply the patch. Otherwise, it applies the patch when the task returns to user space, because when it's in user space, it's not executing anything in the kernel and is therefore safe. So here I have a test patch just to modify proc devices. So very simple patch. Not really terribly interesting, but it has a visible effect, which is nice. So if I successfully live patch, there will be devices at the beginning of proc devices. So with Kpatch, I looked at Ubuntu 2004, and I tried doing an apt-get of the Kpatch build tools and building against that. And very similar to with Zen, I need to give it a path to the VM Linux. So the original symbols, I need to give a source directory, a configuration, and then finally my devices. When I kicked this off at 5 p.m. one evening, I came back at 8 p.m. and it still wasn't done. And I'm like, well, maybe it just takes a long time. And I came back in the morning and I discovered it was still running. And this was not something I expected, so I decided to attach GDB. I turned out that there was, it was performing an fscanf of module.simvers from simvers.read. I looked at the offending line, and it was doing a while fscanf is not end of file. If fscanf does not convert anything successfully, it doesn't increment the file pointer, so it just stays there in a type loop, doesn't do anything, so that's the bug I encountered. I looked at the upstream build tools at simvers.read and found out that this was a bug that they had fixed in upstream, so then I went and I did user local bin kpatch build tools. So I got a working patch then, and then I had a beginner mistake where I did not notice that the source that I was building did not match the source I was running, because apt-get source got the latest Linux source. Having fixed that, I was able to generate a live patch successfully, so this is very similar to the Zen build process, and was able to load it. So it loads as a normal Linux module. It waits up to 15 seconds for the transition to complete, and it is patched. So, huzzah. All right. So to summarize this presentation, live patching is very fast compared to other software update options. It's typically performed via a trampoline. Live patches may need to be specially coded. You can't just take a random bit of source and expect to be able to generate a live patch from it. And don't assume that live patch tooling will work with any particular software compiler version. You really need to test. So thanks to Allison, Vadim, and Luke for early feedback on this presentation. I have some references here.